Hi, I'm Riyadh. I'm going to tell you about a new cryptographic primitive that my co-authors and I constructed that gives a super compact, super efficient way to verify that many parties agree on a fact. For example, imagine that many computers on the internet all see an attack originating from the same IP address. Or maybe many different people see a rare event, like a huge meteor streaking across the sky. Or maybe many different players on a blockchain all have some notion in their head of the chain's state. In all of these cases, it would be great if these parties could collectively attest to their common knowledge. In other words, the parties want to generate a certificate that, say, a majority of them agree on some event. Naively, we might just ask each party to generate a digital signature and then collect all of those signatures into one certificate. Unfortunately, the problem is that as the number of parties grows, this approach gives us huge certificates that are extremely expensive to check. Instead, what we want is a certificate that is small and easy to check, even if the number of parties is huge. But we want some stronger properties too. Maybe it's not just that there are many parties. Maybe some of the parties are more credible than others, so we assign their opinions different weights. So a supercomputer might get a lot more weight than the gaming rig in your basement. Or maybe we might worry that some of the parties are faulty. For example, we might worry that when some people see a meteor, they actually think that it's a UFO. Or even worse, some of the parties could be malicious. For example, maybe the person in the threatening hoodie tries to convince us that actually they own all the money. To solve these problems, we introduce a new cryptographic primitive called a compact certificate scheme, and we give an efficient construction that is general purpose, supports many parties of different weights, and doesn't require trusting the parties or the person who creates the certificate. Our evaluation shows that at 1 million parties, our construction gives certificates that are 50 to 280 times smaller and 300 to 4,000 times easier to verify than the naive alternative. And we show how this construction can be deployed in a distributed setting, namely a blockchain with stake-weighted voting. In the rest of the talk, I'll define compact certificates, tell you about our construction, and then show you some evaluation results. For starters, let's talk about the setting. Throughout the talk, I'm going to be using the running example of many parties signing the same message M, though remember, compact certificates apply to any NP statement. We'll call these parties attesters, and we assume that each attester is assigned a weight. The attesters in this picture, for example, have weights ranging from 1 to 9. Remember, the idea here is that we want to be convinced that many attesters signed the message M. In particular, we'll say that we want signatures totaling some target weight, which I'll denote capital T. For example, say our target weight, T, is greater than 21. Then we would be satisfied if we were convinced that, say, the left 3 people in the picture signed, since in total their weight is 22. Of course, any other combination of signers with sufficient weight would also work. To solve this problem, we defined compact certificates, cryptographic protocols between a prover, which I'll write blackboard bold P, and a verifier, which I'll write blackboard bold V. In this protocol, the prover knows all of the attester's public keys and their assigned weights, and the verifier knows a short commitment to the keys and weights. The prover's goal is to convince the verifier that it knows signatures on a message M whose total weight is greater than some value T. A compact certificate scheme has 2 properties. First, compact completeness means that if the prover indeed knows sufficiently weighty signatures, it can convince the verifier of this fact using a certificate that is very short, in particular, at most polylogarithmic in the total number of attesters. Second, proof of knowledge, informally, means that any prover who generates a convincing certificate actually knows a sufficiently weighty set of signatures. Here, knowledge is defined in the usual way, in terms of an extractor algorithm. Now our goal is to construct a concretely efficient scheme. We'll build this scheme based on Merkle trees. The high-level idea here is that the prover creates a Merkle tree that contains all of the attester's signatures and sends the verifier the root of this signature tree. Then the verifier challenges the prover to reveal a few random signatures, and it checks them. Pictorially, the prover starts with some signatures and constructs the signature Merkle tree, whose root is capital R. It sends R to the verifier, who chooses a set of challenges and sends them to the prover. The prover responds with the signatures in the leaves corresponding to each challenge, plus the Merkle path authenticating that leaf against the root R. And finally, the verifier checks all of the signatures and all of the authenticating paths. This description glosses over two important details. First, how does the verifier learn the public keys corresponding to each signature? And second, how can the verifier efficiently sample the challenge leaves it requests from the prover? I'll answer each of these in turn. First, let's talk about public keys. Remember from the setup that the verifier does not know all attester weights and public keys, just a short commitment to them. In this construction, that commitment is the root of a Merkle tree whose leaves contain the weights and public keys corresponding to each attester. We'll call this the attesters tree with root capital A. This means that for each signature that the prover sends to the verifier, it also sends the corresponding weight and public key plus an authenticating path in the attesters tree. It's important to note that since the attesters tree is ground truth, it needs to be computed ahead of time either by the verifier or by a party that the verifier trusts. So that takes care of public keys. Now let's think about how the verifier samples challenges. The problem here is we might have a huge number of attesters with very tiny weights and a small handful with very heavy weights. So if the verifier samples uniformly from the attesters, it needs to get very lucky for any of its samples to have high weight, and therefore it needs a lot of samples and a big certificate. Intuitively, what we want instead is for the verifier to sample attesters' signatures in proportion to their weight. Specifically, define capital S to be the total weight of signatures on the message M that the prover knows. Now, we partition the range from 0 to S into subranges, one for each attester who signed the message M. Pictorially, we have the range 0 to S divided into segments whose length corresponds to the weights of the attesters. Now, the verifier can sample a value Z in the range 0 to S and request the signature that corresponds to the attester whose subrange Z falls into. For example, if the verifier chooses the value of Z I've drawn here, then it would request the signature from the attester whose public key is PK3. But there's an issue here. Remember, the verifier is only allowed to receive a tiny amount of information from the prover, certainly not enough to write down all of the subranges of all of the attesters. So how can the verifier execute the sampling procedure that I've just described? The idea is the prover commits to those subranges as part of the signature Merkle tree. Specifically, let's denote the lower end of each attester's subrange as capital L. So capital L sub 1 is 0, L sub 2 is W1, L sub 3 is W1 plus W2, etc. Now, to generate the signature Merkle tree, the prover commits to both a signature and a subrange starting point in each leaf of the tree. When the prover opens a leaf in response to a challenge Z, the verifier checks the signature just as before, but it also checks that the committed range actually covers Z. That is, that Z is between L sub I and L sub I plus W sub I, which is the attester's weight. Recall from a few slides ago that the verifier can learn that from the attesters tree. This might be slightly surprising. It means that the verifier does not need to check that the prover generated all of the subranges honestly. So we might ask, wait, why does this work? Well, in essence, if the prover exaggerates the value of S, in other words, if it claims that it knows more total signed weight than it actually does, this means that the prover must commit to at least one leaf in the signature tree that the verifier would reject. More specifically, there must be some index I such that the value L sub I plus the corresponding attester's weight, W sub I, is less than the value L sub I plus 1, the next subrange start. This means that if the verifier sends a challenge Z that is greater than L sub I plus W sub I and less than L sub I plus 1, there's simply no leaf in the signature tree that would cause the verifier to accept. So in sum, if the prover is dishonest about any of the subranges, then with a sufficient number of queries, the verifier will detect and reject. Now we can write down the full protocol. The prover starts with knowledge of signatures having total weight at least S and all of the attester's public keys and weights. The verifier knows the message to be signed, the root of the attester's tree, and the target weight T. The prover builds a Merkle tree of attester signatures and subrange lower bounds. Then the prover sends the root of the signature tree and the claimed total weight S to the verifier, who samples challenges Z sub I from the range 0 to S and sends them to the prover. The prover sends the corresponding leaves in the signature and attester trees along with their authenticating paths, and the verifier checks everything. The claim total weight is at least the target weight, all the signatures and Merkle paths are valid, and all the challenges are correctly covered by the subrange lower bounds and attester weights. Finally, since this protocol is public coin, it can be made non-interactive via the Fiat-Shamir heuristic. In the paper, we show that this protocol is a non-interactive random oracle proof of knowledge, as defined in the work of Bensasson, Chiesa, and Spooner from TCC 2016. More specifically, we show that for lambda bit security, the number of queries is proportional to lambda and inversely proportional to the log of the ratio between the total signed weight and the verifier's target weight. Interestingly, this means that the more signatures the prover knows, the shorter a certificate it can create. We'll see the effect of this concretely in just a moment. This also means that the certificate size is indeed polylogarithmic in the number of attesters, as required by the compact completeness property. In practice, the size of the certificate is dominated by the authenticating paths for the Merkle trees. With that in mind, let's take a quick look at concrete performance. We implement our scheme in 1,200 lines of Go, including several optimizations that we describe in the paper. Signatures use ED25519, the hash is SHA-512, truncated to 256 bits, and we use MessagePack for serialization. In our evaluation, we compare against the naive baseline I described earlier, namely bundling together signatures whose total weight is the verifier's target T. In the first experiment I'll describe, we explore the effect of target weight T and total signed weight S on certificate size for 1 million attesters and 128-bit security. As the target weight T goes up, so does the size of the certificate. Meanwhile, as the total signed weight that the prover knows goes up, the certificate size shrinks. Concretely, certificate sizes range from under 100 kilobytes to roughly 900 kilobytes, for target weights ranging from 10 to 70%, and total signed weights ranging from 5% greater than the target weight to 100%, i.e. all attesters signing. In contrast, naive certificates range from 11 to 77 megabytes, depending on the target weight. In other words, about 50 to 280 times larger than a compact certificate. In the second experiment I'll mention, we look at certificate verification time, fixing the target weight at 50% and varying the number of attesters from 100 to 1 million and the total signed weight from 55 to 100%. As the total signed weight goes up, the number of verifier challenges, and thus the number of signatures that the verifier must check, goes down, with correspondingly reduced verification time. Interestingly, the verification times for 10,000 and for 1 million attesters are essentially the same. The main difference is in the cost to verify Merkle paths, and that's low order. Concretely, verification time ranges from slightly under 10 milliseconds to just about 80 milliseconds across this parameter range. In contrast, for the naive baseline, checking a certificate made by 100 attesters is slightly faster, but checking one for 10,000 and especially for 1 million attesters is much, much slower. For 1 million attesters, the difference in performance is a factor of 300 to 4,000. As a final note, the cost of generating a compact certificate, which I haven't shown here, is also pretty reasonable. For 1 million attesters, the cost is under 60 seconds on a single thread. The predominant cost is verifying all of the attesters' signatures in order to determine the total signed weight, and this is easily parallelized. In total, generating a compact certificate is at most a factor of 2 more expensive than the naive baseline. To quickly recap, in this work we defined a new cryptographic primitive called a compact certificate scheme. We gave a concretely efficient construction for Merkle trees. For 1 million attesters, this construction gives certificates that are 50 to 280 times smaller and 300 to 4,000 times faster to verify than the natural baseline. And although I haven't had time to talk about it today, in the paper we discuss the use of compact certificates in a distributed setting, namely for blockchains with stake-weighted voting. Thanks very much for your attention.